Hi, I'm John Colgrove. I'm a co-founder and CTO here at Pure Storage. In a flash array, data reduction is extremely important because the flash costs a lot more than a disk. Byte for byte, it costs a lot more, but it gives you a lot more IOPS. So one of the things that we do is we trade off a few of those IOPS in order to lower the cost using data reduction techniques. Compression, deduplication, and fine-grained thin provisioning are the three techniques that we use here at Pure. One of the great things about flash with data reduction technologies is you don't really have the same performance penalty. If you think about deduplication, for example, deduplication is fundamentally about randomizing your data. I go to write some data, and the system figures out that this piece of the data and this piece of the data are really already stored over here and over here. So what deduplication does is it takes my nice organized chunk of data on disk and turns it into a few separate IOs scattered around the disk. That's a killer for disk. I mean, disks suck at random IO, and that's exactly why you don't want to do deduplication on disk. With flash, you don't have those kind of random performance penalties. So with flash, when I take this same data and I dedupe it into pieces here, and a main chunk of it's here, and another piece is over here, I don't pay any penalty for accessing it. It makes flash the perfect technology to really take advantage of deduplication. At Pure, because the flash is so expensive, the first goal that we have is always to save every byte that we possibly can. So with our deduplication, one thing is it's global. It's across the entire array. That's a huge scalability challenge, which fortunately we've managed to meet in using the same technology that we have used for our fine-grained mapping. Now with that, what that means is on any one of those controllers, any block that you write, if a 512-byte disk sector matches some other 512-byte disk sector that is stored on the box, we will eventually find it and deduplicate it to save that space. If there's 2 copies of the block in the array, they will fairly quickly become 1 copy that's stored. As we get some very highly deduped sectors, we can run into issues where, gee, if we lost this one sector, we're losing thousands and tens of thousands of pieces of data. One of the things we do is we take those really highly deduped blocks, we pack them together as we optimize the array, and then we put extra protection on it so that they are even more robust than the regular blocks. So doing a fine-grained mapping of potentially a petabyte or more of storage at a 512-byte level is a difficult engineering problem. It means that we have literally trillions of potential entries in our map. That's both in the map we use whenever you go to read data and we have to look up and find where the data is stored, as well as the map where we have to look up dedupes. One of the things that we've done, and this goes back to a fundamental thought that we always have in Pure, we rethink the problem from the ground up for flash. We don't look at the way people have done it in storage before. And to be perfectly honest, we've looked to some of the super scalable websites for inspiration in some of the data structures and techniques that we've used. So what we have is a very fine-grained mapping structure at the core of our product. And that very fine-grained mapping structure is what lets us both do thin provisioning. If you have not written a 512-byte sector, we will not have allocated it. If you have written just a pattern of data, all zeros or all ones or all spaces over a 512-byte sector, we will not record that. Instead, in our map, we'll just record that pattern. And we can do that at a very fine-grained level because we have this basically append-only flash-oriented mapping structure that we use for both our dedupe lookups as well as for our regular block lookups when you're reading and writing data. The net result is that with virtual machines, you'll tend to see probably a compression ratio in the neighborhood of half to 2/3 of the data will get compressed, and then you'll see a dedupe ratio that can often be 5 or 10 to 1. So you might get 10 to 1 on dedupe, and then take that 1/10 and compress it another half again due to compression, and there's 20 to 1 data reduction. We've had customers that have seen as high as 30 or 40 to 1. We have other customers that see 5 or 6 to 1. Databases, you tend to see some very nice deduplication on updates that people didn't realize was there. It actually saves writes. The database writes an 8K record. You've made a small modification to some record in the database, so this 8K buffer that it's writing, only a little bit of it's changed and the rest of it's all the same. We get rid of those writes. So it saves us writes, it saves us wear and tear on the flash, and that's another way that dedupe helps us reduce writes. I think most people will usually see on an application something between, let's say, 5 and 10 to 1. And if you go over 10 to 1, it's just the cost is so cheap at that point that it's just gravy.